Good evening, everybody, and a very warm welcome to this evening's lecture on the future of the universe by Professor Somak Raychaudhury. It's a great pleasure and a privilege to have with us Professor Somak Raychaudhury, who happens to be my longtime friend, one of the leading scientists of India, and now the director of the famed Inter-University Center for Astrophysics and Astronomy. Now, and there is obviously a lot of interest, as is evident throughout this room, in the future of the universe, which is a nice thing. It's not possible to give an introduction to somebody like Somak, because to put it very simply, he's a star who observes and writes about stars. So that's the only one sentence introduction that I can think of. But for those who do not know of his antecedents, I'll just give a brief outline of his career. He is, as you know, the director of the Inter-University Center for Astronomy and Astrophysics, IUCA, in Pune. He graduated from Presidency College, University of Calcutta, with further studies at the University of Oxford, UK. After his PhD from the University of Cambridge, UK, he taught at Harvard, where he was part of the team that built the Chandra X-ray Observatory for NASA. After teaching for over a decade at the University of Birmingham, UK, he returned to India as the head of the Department of Physics and as the Dean of Sciences at Presidency University, Kolkata, before he became the director of IUCA. His research involves a wide range of topics in observational cosmology and astrophysics. He's a fellow of the National Academy of Sciences in Allahabad and the Royal Astronomical Society in London. And so, without further ado, I would request Somak to come up and talk about the future of the universe. So, ladies and gentlemen, please join me in welcoming Professor Somak Raychaudhury.
Thank you very much, Anton. And after that introduction, everything will be anticlimactic, of course. I'm an astrophysicist, a cosmologist, and that means that I work on some of the largest questions in the universe. Not necessarily the most important questions, but the largest questions, which means, we work on the universe as a whole and ask questions like, where did the universe come from? How old the universe is, where it's going, and what is in it. So I'll touch upon almost all of these to some extent today. But it is also a subject that is rapidly evolving. So a lot of the stuff that I'm going to talk about, you will have heard of in various articles and things on the web. But this is not textbook material, because this is happening now. And as you will see towards the end, I will be the first to admit that we don't have a clue as to what the answer is. We don't know what the answer is. But the fact that we can ask these questions about what's going to happen to the universe in billions and billions of years, not 100 years from now, not 10 years from now, but billions and billions of years, and actually address these questions based upon the laws of science that we know from our laboratories, is a giant leap of faith, and also a giant arrogant experiment to some extent. Now, we do believe that we can use our own sciences, the laws of physics that we know from our laboratories, and apply it to the universe. And it works, right? It works in many ways. And using that, we are asking the question, what happened to the universe? Where did it come from? And where we are going. So I acknowledge the fact that today I see a lot of young people here, which means we do have a lot of people who have been exposed to several of these topics. But the audience is pretty heterogeneous. So I'm going to start from really the basics. And so bear with me if you already know a lot of this. Okay? But I'll try to, first of all, start motivating you about our subject. So now, as an astronomer, what we do is we look at the sky, right? So you can see that if you look at the sky from a place which is not Victoria Memorial, but go away from Kolkata and look up at the sky, you'll see it like this. And what you see in there are stars, right? So if you look up at the sky, and even through a small binocular, small telescope, you see a lot of stars. And these stars twinkle. Now, if you do the same thing and take a large telescope, and for me, a very good telescope might be the Hubble Space Telescope that is in space, and you concentrate on, say, a small part of the sky that's maybe the size of the moon, or something like that. Something like that. And look at this. This is an actual picture of that part of the sky, but taken with a large telescope. Okay, so there's a big difference between this picture and that picture. What is the big difference? This picture, everything, every single object there is a star. A star like our sun. Maybe bigger, maybe smaller, but they're like a sun. Every single object in this picture, except for two, 1 and 2, those two are stars. But every single object other than those two in this picture is a galaxy. A galaxy has 10 to the power 11 stars. Right? So we're talking of 10 to the power 7 is a crore, and we're talking of 10,000 crore stars. So the difference between that little speck and that little speck here is that there are 10,000 crore of those in one of these. And these are the things that the universe is made of, not those things. These are made up of those things. But the universe is made up of galaxies. And this is something that we did not know till the 1930s, as late as that. Right? So remember, Rabindranath died 1941. Einstein published his theory of relativity 1915. Around that time, this was not known very well. This is a very, very new subject. Very new subject. And because we did not know what the universe is made of, we had no idea what the universe, where it came from and where it is going. So this is something that's happening now. So actually, let me tell you a little bit of history of how we got to know these galaxies. And I'm going to introduce you to two very interesting characters. One of them is William Herschel in England, a German who lived in England in the late 18th century, and a Frenchman called Charles Messier, who also lived in Paris in the late 18th century. They were contemporaries, they did not know about each other. Right? And they both used small telescopes that they built themselves to look at the sky and try to figure out what was happening in the sky. And they both independently realized that there were many different kinds of stars in the sky, and some of them were point-like objects that twinkled, twinkle, twinkle, little star, and there were others that did not twinkle, but they were fuzzy. That's why I've called it fuzzy objects in the sky. Now, they're very interesting people. Herschel was a musician. He was actually an organist. There are lots of compositions of Herschel for the organ. He was an organist of the organist of Bath Cathedral. And he had emigrated from Germany to as a musician. And as a hobby, in his backyard, he built telescopes. Actually, he built the largest telescopes in the world as a hobby. Can you do that, you think, now? And he lived with his sister, Caroline Herschel, who was a soprano. She was a singer. And she was always complaining that this man, my brother, is making the house entirely dirty. He brings all these huge sheets of metal lying in the bedroom. I trip over them, and he's building these telescopes, right? In the end, I won't tell you about Caroline Herschel today, that's another talk. Caroline ended up being a better astronomer than her brother. She discovered quite a lot of comets, stuff like that. So Herschel built the largest telescopes in the world, and as a result, he started looking at the sky and he found some very interesting things. Now, Messier, on the other hand, in France, was also observing the same sky for a different reason. The King of France, around 1780 or so, had announced that there would be a cash prize for anybody who discovered a comet, because comets were supposed to be astrologically very important. I'm not asking you to believe in astrology, but some people do. And superstition means that once a comet comes, something devastating happens, right? So the king announced that there will be a cash prize, and so people were sending in entries saying, I've discovered a comet, and it turned out that they were all wrong. Because people looked through a telescope, saw something fuzzy in the sky that looked like a comet, sent something in, and actually they were not, because some stars were like this. They were fuzzy. So the king asked Messier, who was the leading astronomer in France, look, can you make a list of fuzzy things in the sky that are not comets? So Messier made this list called the Messier Catalogue, which anybody here who has done astronomy as an amateur astronomer with a telescope knows the Messier list. There are 110 of them, and these are the easily seen objects that you can see naked eye or with a binocular in the sky, a star that doesn't twinkle. There are 110 of them. I've taken 4 of them here, just to illustrate a certain point. And that is the reason why astronomy did not take off as a subject till the 1930s. And what is the reason? The reason is that it is a very difficult task to figure out how far away something is. And this is the kind of thing that we did not learn how to do till the middle of the 20th century. Okay, so think of the sun and the moon. They're the same size on the sky. If you believed that things that are the same size on the sky, they're exactly the same size on the sky, right? Half a degree. If you believe that they are the same thing, then of course you're completely wrong. Sun and the moon are not. One is 800 times bigger than the other, but one is 800 times more further than the other. That's why they look the same size in the sky. So the reason why all these people were looking at the sky and not figuring out that these are stars or not, are they single stars? Are they collection of stars? Why don't they twinkle? These questions were being asked because nobody had any idea how far away these things are. So now, with superior telescopes, I can show you what was puzzling them. Because as I said, the problem is old. So here are 4 objects from the Messier Catalogue. All 4 were discovered by Herschel. He gave them different names. He called these things nebulae. Nebulae comes from the word for cloud, cloudy things in the sky. So here's M1, Messier 1. It's known as the Crab Nebula. And it is the remnant of a star that exploded on the 4th of July, 1054 AD, about 1,000 years ago. We know this because there are very good records of that explosion happening. When that explosion happened, there was no night for about 2 weeks. Because when a star explodes, it produces so much light that you don't need the sun. Okay? Such things don't happen very often. It happened 1,000 years ago, and this is what it looks like now. Star has exploded, and it's just like an explosion of anything, leaves behind a remnant. So that's why it's fuzzy. And in 1,000 years, it's expanded to become a nebula. That thing is a collection of 1,000,000 stars, 10 to the power 6. And it's the 3rd object in the list. The 27th object in the list is an old star that has lost a lot of its material and has thrown away a lot of gas and dust in the space surrounding it. It's called a planetary nebula. And here is a galaxy, the number 51 object of the same list. Okay? They all look the same on the sky through a small telescope. They're the same size. Yet, this thing has 10,000 crore stars. This is one star. That has 10 lakh stars. And that's one star. Until the 1930s, people didn't know that difference between them. And that is because we had no idea of finding out that this was so many light years away. I'm telling you now because I know it. And this is so many light years away. This is 6,000 light years away. That's millions of light years away. So unless you know how far away something is, there is no way of you knowing how big it is, right? And what kind of stuff there is. And this is that is why we are learning to do this now. And the theme of today, the talk today would be us learning how far away things are in order to figure out how big the universe is. And that is the first thing we need to know in order to know the fate of the universe. So I needed this preamble to make you understand how difficult this thing is and how new this thing is. So we just said the universe is actually made up of these things, galaxies, and these things are made up of these things, right? So there are thousands of crores of these things in a galaxy, and single stars are like our sun. We know one of these stars very well. They're nearby, and so you know what a star looks like. Right, so the universe is made up of galaxies. I'm just showing you the same picture again. All of these are galaxies. Just like any matter is made up of molecules, something that you learn in school, the universe is made up of galaxies. These are the basic building blocks of the universe. There are many galaxies that look nice and round. These are called elliptical galaxies. Most of the galaxies, about 80% of them, are nice and flat, and they are rotating very fast, and they have nice little spiral structures in them. Anything that rotates, if you take a cup of tea and stir it, you will see this kind of pattern in it. Right? You can see these things rotate. Our galaxy is like this. What does our galaxy look like? We live in something like this. Right? Our galaxy we call the Milky Way, Akash Ganga in Indian languages. And this is what it looks like. Now, this cannot be a picture, of course, because we live in it. You can't take a picture from inside. This is an artist's impression. But there are other galaxies like this for which we've taken pictures. So, here, from the side, it's very flat, looks like just about a chapati, a roti that is just getting a little inflated in the middle. Our sun is nowhere near the center. As you know, for thousands of years, we thought that we were the center of the universe. Everything is being made for us. Nothing, we're in a small galaxy and not even in the center. Here's the sun with our Earth going around it, okay? And right there in the middle. Now, if you look from on top, this is what the galaxy looks like, our galaxy. And the sun is here, and it's going around like that. It's gone around 20 times in its lifetime. The galaxy itself slowly rotates, and the sun goes around along with the Earth around it. In fact, a lot of things happen in the history of the Earth as the sun goes around. For example, as the sun goes around, you can see that there are these spiral arms, and it has to go in and out of them. Also, it has to go in and out. It has a vertical motion. It goes in and out of the plane. And we believe that one of these episodes, when it went very close to one of these and went in and out of the plane, sent a volley of meteorites to the Earth that killed the dinosaurs, for example. So the fact that in the history of the Earth, in the geological history of the Earth, there's quite a lot that can be correlated with the fact that the sun goes around the galaxy is very interesting. Okay? So this is what we look like. Now, think about it this way. The next time you go look up at the sky, you know that what you will do is you are here. And you look up at the sky. You look in this direction or this direction and this direction. You can look in that direction, etc. If you look towards the middle of the galaxy, what would it look like? Because we're in a plane and there are lots of stars there, this will look like a path in the sky, right? A river. That's why it's called the Akash Ganga. That's why it's called the Milky Way. It looks like a way of milk. So this is the Milky Way. When you see the Milky Way in the sky, you can really see it if you're out, away from city lights, a little bit from India. Really, to see the Milky Way, you have to go to the southern hemisphere, because the Earth blocks this part of the galaxy from India and northern hemisphere. From America or from Europe, you can't see the Milky Way at all. But if you look in this direction, what will you see? Because you're in here, you will see stars. These stars. And that's what you see. This is what the picture that I showed you. You see stars in the sky because we lie here and we see, as we look up at the sky in any direction, we see these stars very thinly placed around us. And if you look in that direction, you will see a whole bunch of stars very thickly distributed, right? Here's a good picture of a place I go quite often to, and that's in northern Chile, in the Atacama Desert, on the Andes, one of the places where the best telescopes in the world are placed. You can see, that's the Milky Way. You see all these black spots, these are all dust. In the plane of the Milky Way, you can see that there. In a place like this, when the Milky Way, if you see it in full glory, you can read by starlight. You don't need the moon or the sun, right? It's very bright. The sky is very bright. From India, we are not fortunate enough to see the Milky Way in its full glory. Okay? This is one of the telescopes that I've used in my life a lot, and it'll come back in this story a little later. Now, you see these two things? These two things are also called clouds. These are called the Magellanic Clouds. They are also galaxies. They are tiny galaxies. In the southern hemisphere, you see them naked eye. You just look up. There are like two clouds there. They don't go away. They're not clouds. Just like the Earth has a moon. Saturn has maybe 50 moons. Our galaxy has about 50 such moon galaxies. Very tiny galaxies that go around it. These are two of them that you can see naked eye, right? Magellan, when he went to the southern hemisphere, went around South Africa, discovered these, and they are named after him. And here's what our neighborhood looks like. So here's a kind of a schematic diagram of what we look like. See, this is the Milky Way with all these little dwarf galaxies. There are about 40 or so that we know of, maybe 50. And here some of them are marked. Here's another one, our nearest galaxy, which is called the Andromeda Galaxy. Okay, and they are, it also has all these satellites around it. And we are together in a group. Galaxies don't like to live alone. They like to live in small groups, maybe 2, 3, 4. Sometimes they live in very large clusters, which has thousands of them. Our little group, just if you go outside our galaxy, we have the other one, which is Andromeda. It's actually coming towards us, falling towards us, and us in about 4.5 billion years. I don't think any of us will be there to see it, but you can calculate from its current velocity and distance, etc. So these two are falling. So galaxies interact with each other quite a bit. They merge with each other, they hit each other, they tear each other's hair out, things like that. Right? And so I just wanted to go through a set of cartoons like this to set the kind of scale of the universe. Okay? So I've stolen this from somebody else. I shouldn't have said feet here, but people use meters. But this is taken from an American website, so they are feet. Right. So we in astronomy measure distances in terms of how much light travels in a certain amount of time. Okay. Right. So actually, what happens is that light travels. That's why foot is a good unit to use, but you can use meters if you want. 1 foot in 1 nanosecond. A nanosecond is a billionth of a second, 10 to the power minus 9 seconds. Right? So that's light. So, for example, this room is maybe 3 meters, 10 feet, a little more. Okay? So if somebody gets up from the back of this room and leaves this room, I will not know that for about 10 nanoseconds. Right? Because the information will come to me at the speed of light. Now, my senses have a time scale built into it, which is about 0.1 seconds or something like that, right? And that's why it makes no difference to me. You can leave the room and it appears to me as instantaneous. But that's because this is this room. Imagine what happens if now you do this for the universe. And that is why we measure distances and also velocities, everything in terms of speed of light. So our sun is about 8 minutes away in terms of the speed of light. Okay? So it takes light 8 minutes to come to us, which means that today, if some monster comes and destroys the sun by some reason, some way, we will not know for another 8 minutes. Now, we actually will not know that the sun has gone, so we'll actually go around the sun for 8 minutes, because that information travels at the speed of light also. Okay? So sun is not there, 8 minutes. So now already from here to the sun, you can realize that this is becoming appreciable. The fact that light travels at a certain speed is becoming important. Now, you see that this makes an astronomer's life like a time machine. If you want to see what happened in the past, all you have to do is to look away. Do you get that? Because I'm seeing the sun now as it was 8 minutes ago. I'm seeing the nearest star now as it was about a year ago. Because the nearest star is about a light year away. It's actually 4 light years away. I have no idea what it looks like now. The light has taken 4 years to come to me. And so if the star is gone, it's gone. But I won't know about it 4 years. So I'm just looking further away. So history of the universe comes to me by just looking further away. This is why we build bigger and bigger telescopes. Because we want to know the history of the universe. You build a bigger telescope, you look further away. And then you know something about the past of the universe. Remember, I'm going to talk about the future of the universe. But for that, we need to know the past. So actually, we use another unit called parsecs, but that's what I wrote there. The 1 light year or a few light years is the nearest star. The nearest galaxy, the one that I showed you in that picture from Chile, is about 150,000 light years away. Huge distance. Nearest galaxy only. So when I am looking at it, I'm looking at it as it was when humans were barely humans yet. That's why this picture of somebody maybe living in a cave. Humans were not Homo sapiens yet. Nearest galaxy. Nearest satellite galaxy, not even the big galaxy. The time scale of the universe is huge compared to human time scales. The entire human history fits into the time it takes for light to come from the nearest satellite galaxy to us. And as I said, galaxies live in large clusters. If you go to the nearest cluster, which is like the nearest city of galaxies, that is 65 million light years away. So if I'm looking at the Virgo cluster, I'm looking at it at the time when dinosaurs were getting extinct, 65 million years ago. Now think about the time scale of our evolution, of the human time scale, and the time scales we deal with in the universe. And this is something I can observe even with a small telescope. Messier observed several galaxies in the Virgo cluster through his small telescopes. And so he was observing things that were 65 million light years away already. And now we can observe things that are billions of light years away. Okay? So the universe started, I like this cartoon, as we know, started with what we call the Big Bang. I'm not going to explain the Big Bang to you. It's called the Big Bang. It's actually not a bang, because there was no bang then, no sound. But it started suddenly. That's why it's called the Big Bang. Okay? This is what we now think. It started at a time called t equals 0. And since then, it has been expanding. And now it looks like this. Okay? So I'm going to show you what that means and how we know this. What does that mean? The universe started from a point. Everything that you see in the universe now can be mapped back to that point 13.8 billion years ago. We know the age of the universe very, very accurately now. That's another lecture. I'm not going to tell you how we measured it. But 13.8 billion years ago, the universe started from a point. Don't ask me what was there before then, because I don't know. Nobody knows. But we know what happened after that. Hawking, was one of my teachers in Cambridge, who was there as well, wrote a book in 1988 that made astronomy fashionable. A lot of you in this room may be here because they read this book when it came out. It actually set the standard of all books on cosmology, and it was really wonderful. In fact, I had the privilege of going to the lectures that started this book. He gave a series of lectures called A Short History of Time in 1986, which made this into the book. Now, in the book, he set a few possibilities that the universe could grow into. And this is why it became so interesting. Of course, this was known in the relativity community, in the astrophysics community. But he essentially said, look, there are many ways the universe can evolve from the Big Bang, depending upon what it is made of. Now, here, it's an odd thing to draw, but it's like this. Say you start from a bang, and the way it is done is that the universe is going like this. This is time. It expands, and then maybe it expands forever. Or maybe it expands and then goes up to a point and then comes back together. So Hawking, at the time Hawking wrote the book, all of these possibilities were there. The fact that the universe starts from a bang and then starts expanding and becomes large enough that you can now sit in this room without breathing on each other. And there are so many people on the earth, and there are so many earths and so many stars, etc. Now the universe is very big. Hawking said, now, what's going to happen is that maybe the universe is going to continue like this forever, which is this possibility. Or it could come back altogether and come back into a point. He called it the big crunch. And then, instead of just coasting along, it could go and become a very, 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 very large place and a very cold place, which he called the Big Chill. Now, 1988, and almost all of this has been proved wrong since then, because a lot of the famous experiments to try and verify what Hawking was saying based on what he knew then happened in the 90s and after. And this is the rest of my story. Now, I don't have a clock here, and I have no idea how I'm doing for time. So, no, actually, I've got a clock here. Good. So, for those here who understand graphs, time since the Big Bang, going like that. This is the size of the universe, or any scale of length. And in these scenarios, and this I'm talking of the 80s, when Hawking was writing this book, when I was a PhD student, this is the way we understood the future of the universe, is that we are somewhere here now. It all started from something that was a point, and we are here. And later on, either the universe is going to come back, it's going to coast, or it will expand forever. Now, why is this? See, the universe on the largest scales is governed by the force of gravitation, right? And the gravitation is attractive. We know that. We know that we are on the earth because the earth is holding us due to gravitation. It attracts us. If I throw something up in the air, it comes down because of gravitation. Gravitation doesn't repel like electrical charges do, for example, right? So we come down. And so we know that the universe is full of matter which gravitates. So the idea is that if the universe started off with a lot of matter and energy, with a certain velocity, just like you throw this thing up in the air, the matter of the universe is going to bring it all back, right? Now, is there enough matter in the universe to bring it back like this into a point? Or is there just enough matter to make it coast through and not come back, but not even go faster and faster, like this? Or is there just not enough matter for it to ever have any way of coming back again, right? So that's this. So this was the kind of questions that people were asked. But the natural thing to expect, because there is matter in the universe, is that whatever speed the universe started off with, it will slow down. Because matter slows things down. The little thing you throw in the air starts with a little speed and it slows down. If it has enough speed, it could escape the Earth, but it's still slowing down. Or it will come back. So the universe should be like that, right? And this is what we believed when I was a PhD student, not so long ago. I'm not that old. So how did we do this? So here, people here who are not familiar with the way astronomers work, and there may be a few. I just said I'm going to go into the basics. The basic tool we use is to measure the spectra of galaxies. What is a spectrum? You take light, pass it through a prism. Again, something people learn in school, and what happens, that breaks up into colors, right? Yeah, and the color is a continuum of colors. There are no 7 colors in the rainbow. There are many, many, many colors in the rainbow. It just splits up. So you take the spectrum of a star or a galaxy. Basic bread and butter of astronomy is to take a spectrum of something in the sky through a spectrograph, which might have a prism, might have a grating, and then analyze what's in it. That tells us a lot of things. What does it tell us? It tells us these things. First of all, it tells us what it's made of. Right? So all of these elements that we are made of have a signature, a barcode in its spectrum. So that's what the spectrum of helium looks like. I look at a spectrum like this, and I know it's helium. Right? It's like a thumbprint. Mercury looks like this, your mercury lamp outside on the road. Sodium, neon, etc., right? Okay. So, for example, I take a spectrograph, and this was being done in the 1860s from St. Xavier's Observatory by Father Lafont in Kolkata. So he built the first spectrograph with a telescope here in India, and you probably know that helium was actually discovered from India 150 years ago, from Andhra Pradesh. From a spectrum of the sun. So spectra are being studied for a long time. What happened was, so you look at this, you take a spectrum of a star or a galaxy, and you look at these lines, and you say, okay, this star is made up of sodium, iron, magnesium, calcium, hydrogen, oxygen, nitrogen, etc. Okay? And it's comforting to know that these are the same elements that we are made of. And they all come from that periodic table. So what happens is that, so what we started doing, and that is why I say 1930s, we started learning how large the universe is and what the universe is made of, is we started taking spectra of these galaxies. These spectrographs and the telescopes became powerful enough that we could point to the galaxies and start looking at these things. And then you can say, oh, that's an oxygen line. That's a hydrogen line. That's a magnesium line. And then you started figuring out that these are the things that are in there in these galaxies, right? So, what happens is that, so this is, for example, a hydrogen lamp that you can use in a physics lab, and it will give you these lines. Now, there's a very interesting effect in physics, which is called the Doppler Effect, which means that if the source of light is traveling at a certain speed, these lines move, which means the wavelength of these lines change. If it's going away from you, the wavelength becomes long. If it's coming towards you, the wavelength becomes short, right? And this is called a redshift or a blue shift. So if you take a galaxy and you take a spectrum and you look at these lines, very easy to discover what these lines are because you know what a galaxy is made of. You'll get the calcium line, you'll get the magnesium line, you'll get the hydrogen line. And if you see what its wavelength is, and you know these from the lab, what its wavelength is, and you look at how it's moved, you know whether it's coming towards us or going away from us. Right? Simple as that. And this was done from the 1930s. And you can see, for example, here is the Orion Nebula. You see these lines, you see hydrogen in there, you see oxygen in there. You go a little further away, and you can see that you can just look at this. Here's a galaxy, and here's another galaxy. It's tiny. You can see it's further away, and look at what's happened to its hydrogen line. It's gone a little further away, right? So this is how we figured out that these things are moving away from us if you're looking at things that are further and further away. Okay? So this is called the redshift. This concept started in the 1930s, and people figured out, and you can see the further you go, that line goes away. So this is the man who started all this, a man called Edwin Hubble. He's a very, very interesting person. Again, if you think that you really have to be trained as an astronomer in order to make a big mark in the subject, there are some really great stories in astronomy for people who've come from all over the place and made a great mark. I just told you about Herschel, who not only figured out that there are nebulous stars, he also discovered a planet, Uranus. Hubble was a lawyer. He was trained as a lawyer. He went to the First World War to fight in France for the US. Long nights in the trenches. He thought law was boring. He wanted to study the stars. He came back to the US at the age of 40, went to the University of Chicago and started learning astronomy. And then his first job as an astronomer was at the Lick Observatory in California. Somebody gave him a spectrograph, said, here's a telescope, point to these nebulous objects that Herschel was talking about 200 years ago, and try and find out what these things are doing, what they are made of. So he started all this. And Hubble drew this plot, which is a very classic plot in physics. It plots the distance of these galaxies. We didn't know they were galaxies. There were these nebulous objects that Herschel and Messier had pointed out. All those things that I've shown you. These are the distances, and these are the velocities. And he drew a line through it. Said, look, things that are further and further away are moving away from us systematically. Right? What I showed you before. I showed you that as things go further and further away, they become tinier and tinier. Those things move. This is exactly what he found. Now, if there are many school teachers here, I can see. If one of your students draws a line through a point like this, you'll probably give them 0. It doesn't look like something you can draw a straight line through. But some things work, because that's what it looks like now. I'll show you a picture of what it looks like now. It's beautiful. Actually, it is a straight line. But he just had measurement errors, and that is why it's all over the place. But this is true. And the only way this can happen, where things that are further away from us are all moving away from us. Actually, there can be 2 explanations. One is nobody likes us, they're all going away from us, which Hubble didn't like. And the second thing is that the entire universe is expanding, and that is why from any random point, you see everything else is going away from us. Okay. So this then became the gold standard of our understanding of the universe, that the universe is actually expanding. The fact that, of course, people then repeated and repeated and repeated, and you'll see modern versions of the Hubble plot soon. So we now know the universe is expanding. How is the universe expanding? Now, this is a picture that you see in a lot of textbooks. And I don't like this picture. What they tell you is that the universe is expanding like a balloon expands as you blow into it. And so if you draw some galaxies on a balloon, the galaxies are going away from each other because the balloon is, which means that the space between them is expanding. That is accurate, except that this is not an accurate depiction, because then you can ask the question, who's blowing into the balloon? And I can't answer that question, right? So nobody's blowing into the balloon. What is happening is like this. And this is something people here who have baked anything, you know that you put a dough together, you put some raisins in it, put it in a microwave oven or something like that, and it expands, and you can see the raisins going away from each other because the dough itself expands, right? Space itself is expanding. The space between us is expanding, and that is why the universe is expanding. The galaxies themselves, which are the raisins here, are not expanding. So that's how we basically understand, right? So now we go back to Hawking's question. Space is expanding, the universe is expanding. So what's going to happen? We are here, are we going to come back? Are we going to go expand forever? or are we going to coast along, right? So this is, I'm standing here in 1990 and asking this question. And just see how much we've learned in the last 20 years. To do that, we have to understand, we have to ask the question, what is the universe made of? Because remember, I told you, to answer that question, you have to know what the universe is made of. Is there enough matter to bring the universe back? Right? So then you can ask the question, is the universe made up of things like you and me? Is the universe made up of the material that makes up planets, stars? Actually, we are all made of the same thing, the planets, stars, etc. And to do that, I'm going to give you one illustration to show that it is not. There are many such illustrations that we have learned about in the last few decades. Now, this is a phenomenon called gravitational lensing. What happens is that if you look at, here you are, from way in the Earth, and you're looking at a very distant galaxy. How are you looking at it? Light is coming to you, and it comes through space and comes to you. Okay, now it is very interesting, and this is a consequence of Einstein's theory of relativity, that as light goes through the universe, if it passes any massive object, it bends, as if the light is being pulled by that object. Okay, so here you are, you're looking from here, and here's a galaxy, and the light was coming like that, it would have gone there, but it didn't. It actually, in the intervening space, there are a lot of galaxies here, and so this has been pulled back towards you. Okay. But what has also happened, I'm not a very good left-hander, also happened is that this light coming from the same galaxy has gone there, and it is bent and come towards you. This happens. And so you get light from the same galaxy from multiple paths. Right? And what happens when that happens is that you see the same galaxy in many different places. And sometimes you see them as a distorted arc, a distorted object, which is composed of many images of the same galaxy. This is a prediction of Einstein's theory, and we never thought that we'd ever see anything like this, but we do. So here is a simulation that one of my friends made of a very famous place in Cambridge, the King's College Chapel. If you had something in front of it that could bend light, this is what it would look like. Okay? So now, if I know what it actually looks like, which we know that these spires would be upright like that, we could figure out how much matter there is in between the chapel and myself that is causing the light to bend. So very directly you can measure the amount of matter that is there. This is just a toy example of this. So for example, if you have a checker pattern like this, and you place a blob of matter that you can't see in front of it, even if it doesn't give out light, you can figure out that it is there by looking at its distorted structure, right? So to go from here to here requires very simple physics, and this is done routinely nowadays by looking at the distortions of objects, which we know what we look like, and then try and figure out what the matter in the intervening space between distant galaxies and us looks like. Here's one of my most favorite pictures in astronomy, and it comes from the Hubble Space Telescope of a cluster of galaxies. And what you can see here is there are about 100 of these little things there which look like this. Actually, this one, this one, this one, and that one are the same galaxy. And you're seeing it in 4 different places. I can prove it to you by taking the spectrum of that galaxy, and actually the spectrum acts as some kind of a fingerprint. And they're in some kind of it's part of a circle, right? And you can see that. Can you see these distorted images? These are all distorted images because the light coming, and these galaxies, that little streak that you see there, that line that you see there, that line that you see there, these galaxies look like this, actually. But because the light is coming to you from very far away, far away through other matter and coming to you here, you see them as these very distorted objects. So the universe actually, if you look very in deep images through telescopes, the universe is more like a mirage. It's not real. None of this is real. These galaxies look like this. They are not. This is actually two images of the same galaxy, and you can see that this is just flipped like that. And you can analyze that. I have had several PhD students who've actually worked on things like this, where you analyze the pictures of these and try and figure out how much matter there needs to be in here in order to produce this kind of distortion. And the answer you get from that is that there is 90% of the universe has matter that does not give out light. And this is what we call dark matter. Because you can see some light coming out of here, but this is not enough to cause this kind of distortion. It needs at least 10 times or even 100 times more matter in some cases to cause this kind of distortion. This is a direct measurement, because all you're doing is tracing rays of light and trying to figure out how much matter you need to make the light bend to cause a distorted image like this. Very, very simple thing to do. Actually, a simple thing to do in terms of the physics. Actually, it is quite a complex exercise to go from the distorted images, try to reconstruct what the unseen matter looks like. And this is the common problem of dark matter. From the 1970s, we knew from many other different things that I have not described today, that the universe is predominantly made of matter that we don't see, that does not give out light. So when we look at the stars, that is only a small fraction of the amount of matter that there is in the universe. Good, so we are making progress. I asked the question, do we have enough matter in the universe to bring it back? And the answer is there is a lot of matter in the universe. Stars are a minority. We are a minority. There's quite a lot of matter in the universe that is so much more than the matter we see in stars and galaxies. Is it enough? So, 95, not so long ago, I mean, I'd finished my PhD by then. But around that time, we believed that, okay, the universe is made up of dark matter, and about 10% of that we see, and 90% we don't see. And something happened at that time. And that's the rest of my story. So here's Hubble's law. As you see now, in 95, it's much better. It's not that whole scatter that you saw of the same galaxies that Hubble had measured, but measured with a much better measurement. And we saw that the distance is proportional to the velocity of the galaxy, and you can actually draw a line through it, and then you can say it's actually a line. Okay? And this tells you, and the slope of that gives you a certain quantity that actually gives you the rate of expansion of the universe, that gives you some idea of the age of the universe. 1995, this is what it looked like, and we are asking the question, I told you at the beginning, if you remember, if you look further and further away, you're looking at the past of the universe. So here, megaparsecs are millions of, a parsec is about 3 light years, a megaparsec is 3 million light years. You're looking up to there, and you can see that the expansion of the universe is linear, which means it's constant. The expansion of the universe has been expanding constantly for the last few million years. Now, my question is, how is this expansion going on? Okay, is the expansion slowing down? Didn't I tell you that because there's gravitation in the universe, you're throwing up something, it will slow down because there's matter, right? So this means that if you look in the past, the universe would have been expanding faster, right? The slope of this line tells you the rate of expansion of the universe. And up to there, it looks like it's very constant. The question is if I go very far away, would it go like this? Would it go like that? Okay, so it means if the universe was expanding faster in the past and it's slowing down, anybody guess where this would go? This would go up there, like, because the expansion rate of the universe would go up like that. But we could not pursue that because I told you the biggest problem we have is measuring distances to galaxies, and we did not have any technology to measure distance to galaxies beyond the nearest, say, 100 or 1,000 galaxies. And we found something in 1995 that changed the whole game. And I'll take you another 5 minutes to explain this. What you do in order to find distances in the universe is you need to find a certain standard, right? For example, if you know how large this is, and you look at it further and further away, you can look at its size and you can say how far away it is, right? These are called standard candles. If you know that something you know how bright it is, and you're looking at it, its apparent brightness, you can figure out how far away it is. If you take a 100-power bulb and you place it at a mile away, a kilometer away, you can figure out how far away it is by looking at how much light you're getting from it. And this is the kind of thing that we use to find distances in the universe. So we found in 1995 a method to find very accurate distances of very, very distant galaxies. And that changed the game. And this is the last part of the story. So what happens is, I told you about the Crab Nebula, remember? I told you about the Crab Nebula, the star that exploded in 1054 AD, at a time when that happened. For 2 weeks, there was no night. What happens when a star explodes at the end of its life is that it gives out enough light to outshine a whole galaxy. Here is something that happened in our neighboring galaxy, that Magellanic Cloud I showed you, the one that is a satellite to our galaxy, happened in 1987, and there was nothing like there, and suddenly at one night, one star exploded. It was seen independently by 2 people, one in Australia, one in Chile, looking up at the sky and said, "Where did that star come from?" Right? So you can actually see them naked eye in nearby galaxies. In faraway galaxies, these things can be seen like this. Suddenly, something will appear, and then over months, it will go down. And in 1995, we discovered that that is a standard candle. One type of supernova, it's called supernova type 1, in which the whole star explodes, leaves nothing behind, and you can figure out whether it's of that kind very easily. Then, it is like a 100-power bulb. If you can find one of those, and you can find its brightest point, you know exactly how bright it is, and so you can find out how far away it is. Right? And once this was discovered, of course this led to a Nobel Prize recently, to several friends of mine, we learned the wattage label on the type 1 supernovae. What happens is that, so then we learned what we have to do is to find these supernovae that go out in a galaxy, in a very far away galaxy. You can see them because they're very bright. It can outshine the whole galaxy. It appears something like this. I showed you it appears something like that, and it takes months to go away. You wait for it to reach its maximum brightness, and if you get that, you know how far away that galaxy is, right? So then started this whole campaign from the late 90s, and it's still going on now, and it's yielding these amazing results that I've come here to tell you about. So what you do is you have these telescopes. There are telescopes in Chile, there are telescopes in the Canary Islands, there are telescopes in Hawaii, small telescopes. What they do is they observe the same part of the sky every night, 200, 300 parts of the sky. Come back next night, do the same thing. Come back next night, do the same thing, repeatedly. And then try to figure out what has changed. We are looking for supernovae. And if they find something like this, then they alert the large telescopes like Hubble, and then they follow up. So I'll give you an example. So this is one of the telescopes I've, as I said, used quite a lot. Same one I showed you before. This is the machine, one of the machines that are used now to find these supernovae. It's in Chile. So I'll give you an example of one of these supernovae. Okay? So here is one picture taken by this same telescope, and 3 weeks later another one. Now I'll show you how difficult it is to find these things. Can anybody find out where the supernova has happened? Where? There was somebody there. Where? This, 3 weeks later. Here? There? There? Anybody else? Any other guesses? Just below the galaxy there? Okay, so see, by eye it is very difficult to do this. You can see that anybody will come up with different answers. Very easy to do it digitally. What you do is you actually make the basic level the same. And of course you're taking 200, 300 such images. Each one will have tens of thousands of these objects. You can't do this by eye. So you do this digitally, and you're right. That's where it is. You subtract that from that, you see everything goes away, and you're left away with that thing. Now you can see it. It came there, right? So that's a supernova. That's one of these famous supernovae. We used to at some point give them names. Now we have so many thousands of them, we don't give them names anymore. But now the thing is, once we found the supernova, this is a whole star that has exploded in a galaxy that's billions of light years away, right? And we are seeing them as it was billions of years ago. Doesn't matter. What matters is that we have found them. Now we have to wait till it reaches its peak and then starts going down again. Once that happens, we know the wattage. So we know how far away this galaxy is. So now we can extend the Hubble plot. Okay? We can go out in distance, measure its redshift is very easy. So once you do that, you put the Hubble Space Telescope on it, and you can actually find the little supernova. This is taken with a small telescope. This is taken with the Hubble telescope. You can see that's the galaxy on the outskirts. You had that little supernova star that exploded. You pin on it. You look at its chemical composition. From its spectra, you know exactly what kind of a star it is. Okay? So here's Hubble's plot in 1929, which I said is going to be a failed class exercise now. This is what it looked like in 1995 with the best measurements. Now, the entire Hubble's plot would have fit into this real little yellow blob there. So in 1995, we are going much further away, before the supernova kicked in. And you can see that the expansion of the universe is still pretty constant out to a certain distance. Now comes the moment of truth. What happens after that? Is the universe slowing down? Because then this line will curve. After 95, when we started looking at the supernovae, this is what it looked like. So what happens is, and that entire plot that I showed you would fit into that yellow thing here now, because the supernova enabled us to go much, much further away. And instead of going this way, which meant that the universe was expanding faster in the past, we now know that it's going this way, which means that the universe was slower in the past. Now that took us completely off our expectations. We did not expect this. Gravity slows things down. So, the big surprise about the universe came to us in the end 90s, beginning 2000s, and still we are working on this. We now know that the kind of matter that we are made of, you and I and the stars and the planets and the tables and the chairs and the armadillos or whatever, is the yellow bit. The dark matter, which is the matter that you don't see, that is not made up of the things that we are made of, is the red bit. Until 95, we thought that was the whole universe. We now know 72% of the universe is made up of something else. And that does not gravitate. That does not pull, but pushes. And that's why the universe is accelerating. The universe is getting faster and faster and faster. Now tell me what Hawking would have told you in the book, where he thought that the universe could have enough gravity to bring it back again. If the universe is accelerating, the universe is getting faster and faster and faster, and the predominant matter, quote unquote, in the universe does not obey the law of gravitation. It actually pushes. Space itself in between the galaxies is pushing the galaxies apart and making it faster and faster and faster. Then you can only guess what the future of the universe will be. So we call this dark energy. This blue bit is called dark energy, for want of no other name. I think it's a very bad name. In fact, I gave a talk like this somewhere when an old gentleman got up from the very back and said, "But why do you give it such a negative name? It looks like dark energy in between us could be overcome by all the light within us." So dark energy is a bad name. Dark matter, dark energy. It's because it is not like matter. Matter gravitates, pulls. This is, you know that Einstein has told you that matter and energy are the same thing, E equals mc squared. This makes up the universe, but it's not matter. So the universe is made up of matter and energy. This part is us. By us, I mean things that we see, our stars, our planets, our galaxies. All that at the beginning of the talk an hour ago, I told you makes up the universe. It doesn't, because this is what it does. And this is the gravitating part of matter that makes up the universe. Together, it's only 25%, 28%. The rest of it is, now we know, is something that pushes the universe apart. And so, just like in a tree, you can see as you go in the way the tree has grown, in the universe we can do that. And the implication of this dark energy means that now the universe is going to expand forever. There is no coming back. But not only is it going to expand forever, it's going to get faster and faster and faster and faster and faster. So the universe is going to be a very, very, very lonely and cold place. It's a very sad way of ending a talk. But that's how we know. But the good thing is, that gives us something to understand. Where did this come from? Again, astronomers and physicists are not good at naming things. So they've called it quintessence, this thing called dark energy. The other name is quintessence. This comes from the original Greek word for the fifth element, which they thought heavens were made of. Not right, but okay, that's what we think, right? So again, the future, as I said, Hawking thought we're coming back, or marginally bound or unbound. Now we know that what will happen is what we called not the big crunch or the big bang, but called the big rip, which means that the universe is going to go very, very, very fast, very big, and in the end up being a very, very cold place, right? This is all we know now. I can come back to you 10 years later and tell you the next part of the story, but this is a very rapidly evolving story. And at least tells you that we can have begun to understand what's going to happen to the universe. I'll stop here.
Taking questions, sir. Are you taking questions?
Yes. Sorry, I went over about an hour or so, so I don't know how much time you have, but I'm very happy to answer.
We have time, yes. Please.
Yes.
The floor is open.
Is this repulsion something we tie with the lambda force?
What do you mean by the lambda force?
That in the force which Einstein is.
So that's a very, 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 very good point. So actually it turns out that it's very, very uncannily close to lambda. Lambda, okay, so Einstein's famous so-called mistake. Einstein did not believe that the universe expands, right? So when in the 1932 Solvay Congress, it was announced by Father Lemaitre, who had worked out Einstein's equations and applied it to the universe and figured out that the only solution that can result from Einstein's equations is that the universe is expanding. And he had got some kind of an idea from talking to Hubble Father Lemaitre was a professor of mathematics at Sorbonne. He had traveled to England to meet Eddington. Then he had traveled to California to see what these measurements were being made in California, met Hubble, and realized that mathematically he had solved Einstein's equations and found that the universe is expanding, has to expand, and Hubble seemed to have figured out a way of showing that it is actually expanding. So he announced this in the 32 Solvay Congress, and after that Einstein got up and said, Father Lemaitre, you are a religious person. He was a Jesuit priest and a fantastic mathematician. You somehow have come up with this idea of the expanding universe because you think that, God created the universe in 7 days or whatever. I don't think you understand physics. I don't believe the whole universe can expand. What is it going to expand into? And in order to stop the universe from expanding, according to his own equations of general relativity, he put in an extra term inside the equations, and that is the lambda term that you allude to, which would cause the universe to stop expanding, right? So to some extent, but that is the thing that we are finding now is just the opposite of it. It's making not just the universe expand, but expand faster and faster and faster. So it is actually minus lambda. And the interesting thing is that if you work out Einstein's lambda, later on, of course, he retracted it, he called it his biggest mistake and whatever. But if you work out what the consequences of that lambda term is, it turns out that it's very, very similar, just apart from that sign, very similar. So its equation of state, etc., the physics of it is turning out to be we actually have started calling it the cosmological constant, which he called it. He called it the cosmological constant. We just have started calling it again the cosmological. So you're absolutely right. It is very close. Why it is the lambda term, we do not know. And whoever finds a physical reason for it, of course, is going to get the next Nobel Prize. And that is going to be very, very interesting. Yes? How can it exceed the speed of light? It can't. Of course, at some point what will happen is that the expansion rate is going to take care of it, right? So it won't. No, of course no. No, it can't. How can? But of course, you're thinking of something that is, okay. From what frame of reference are you thinking about it? You'll have to think about that too, right? So relative to what? Relative to what? So speed of light relative to what? If you're looking at the expansion of space itself, right? There is nothing other than that, which is your absolute frame. Okay, so you have to think about how you translate your idea of a speed, right? Because the speed is always relative to something else, when it's to do with the expansion of the space itself, which is the absolute frame of reference, right? And you'll find that if you do the mathematics, it will take care of itself to some extent. The fact that it won't ever go. Sorry, say that again. I'll repeat his question. Two galaxies.
The frame of reference, if we take the origin at one part of the universe and we take another random part of the universe as the moving object, so will it never expand the speed of light?
Okay, so that is an interesting question, and it is taken care of in the way cosmology works. I mean, this is of course one of these questions. His question was, what happens is that if you take two galaxies. That's right.
So it can R take a value where
big C, it can't. As you can also see that V equals HR only happens over a small volume of space, and that itself, that equation will be modified, and that's not a relativistic equation, right? It's a very linear equation. Yeah. So once you look at the distortion of space itself, right, which V equals HR doesn't take into account, then these things take care of itself. I mean, this is how Einstein came up with the idea of space-time being curved, for example, and things like that, the equivalence principle.
So I have another question, sir.
Yeah, but I mean, can I come back to you because there are many other hands up there? Yes. I'll come to you.
Why not the distance in between Earth and Sun is expanding? Because
Very
there
good
is
point.
also
Very
space.
good point. Very good point. Actually, I mean, I don't know how many people. Does anybody like Woody Allen here? Woody Allen had a famous movie called Annie Hall, in which there's a very good scene which I like to show sometimes, in which young Woody Allen, a little child, has given up eating, and the rabbi has come, and they're saying, "What happened? Why aren't you eating?" And he's saying that, "But what's the point?" And he's saying, "Why?" He says, "I just learned that the universe is expanding. So, it will just become bigger and bigger and bigger, and so everybody will die, and so why should I eat?" And the rabbi says, "No, you're stupid. The universe is expanding, but Manhattan isn't expanding." And that is true. Absolutely true. You are not expanding. I'm expanding because you eat too much. But you're not expanding because you're held together by forces of cohesion. These are electromagnetic forces. This has nothing to do with the gravitation of the universe, right? So as the universe expands, things that can pull each other. I told you that the Andromeda Galaxy is coming to crash into us in about 4 billion years. That's because our gravitation is pulling us. We can pull things out of the expansion of space. The cohesional force that holds your molecules together in your own body is much stronger. The Earth's force, that makes it goes around the sun is much stronger than the force that makes the universe expand.
Sir, one more question. Sir, you have just said that gravitation is always attractive. But according to Einstein, if the general theory of relativity, may I conclude the same thing? Because there is no force-like thing.
That question will take me a day to answer. But I might come back to it later on. There was a question here, I'll come back to it. Yeah.
According to what we have learned from you, what was there before Big Bang? Can we think of the situation, what was there before the Big Bang? We can't think.
I think
Now-
I did say at some
now
point in the
there are-
talk, we can't. There is, I mean, in a philosophical sense,
No, okay.
in a philosophical sense, I don't
okay.
think.
Now it is
there is an
expanding and
answer to that.
expanding. So there is space and space everywhere, isn't it? It is expanding only in the space.
Space itself is expanding, right? So
and
space was created. Space
what we
itself
think-
was created at a
as-
time
as
when
we-
the Big Bang happened.
As from the Indian astronomy, etc., we have learned that there are 5 elements. So what is the role of those elements during this expansion?
Yeah, that's a very philosophical,
Not
viewpoint.
philosophical, this is scientific. How? Because you see, the light...
What you call element is not what I call element, right? So these are very different things. Your elements are to do with, the elements of reality. My elements have to do with elements of matter. They're very, very different. Acha, there was I come back to your question. The reason I did not answer your question is that the difference between Newtonian and Einstein relativity is a way of looking at gravity. It's a way of looking at gravity. It's different. So that is a lesson in itself. I mean, you have to undergo a whole course of general relativity to understand the difference between the two. And maybe someday I can talk to you about it. But that's not a question I can answer in a minute. Yes, there's a question there.
Can we have the pie chart? Where
Pie
you are showing
chart.
the composition of
Okay.
the matter.
Yes, that pie chart changes. This is an old pie chart, but it's sort of representative. Yeah,
Yeah, in that yellow,
yeah, pie chart.
in that yellow part, we have all the matter in the universe, right? The ordinary matter we talk about in the galaxies, that matter
Okay,
making us.
so I'll be more specific since you seem to know a little more than most people. We are made up of quarks, right? We are made up of elements that are in the periodic table. They're made up of protons and neutrons. They're made up of quarks. This is called baryonic
Baryons
matter.
and quarks.
The baryonic matter is just protons and anything that is in the periodic table. That is the yellow part. The red part cannot be made up of quarks. It is matter, it's gravitating matter, but because we know the number of quarks that was created in the Big Bang, we know that very accurately. Not something I've talked about today, but we do know it very accurately. We know that all this matter in the universe cannot be made up of quarks. So this is non-baryonic matter. We don't know what it is. We haven't detected it yet. There could be some large particles that could be supersymmetric particles. Particle physicists are working on it. We are working on it. But it is some kind of matter that gravitates, because you've seen the gravitational lensing, right? But it is not made up of protons and neutrons.
Okay.
That stuff is not even matter.
That yellow part, does that include all the light energy, the cosmic background radiation?
Everything.
Is inclusive in that?
No, cosmic background, the energy density is very little. That's
Still, it is
photons.
inclusive.
That's photons. Cosmic microwave background is photons.
Okay.
This is baryonic matter. Anything that has quarks in it. That
Alright.
includes this table, that includes you, that includes stars, galaxies, etc.
Does it include the sum total of the energy also, the light energy, the heat energy? Predominantly light energy.
That
electromagnetic
is related
radiation.
to what we see as baryonic matter, yes.
Okay.
Because the cosmic microwave background you talked about evolved into the current baryonic matter. So they are related. So that includes that.
You were talking, you said that that pie chart is for matter as a whole. But that blue part is named dark energy. Isn't it a kind of a misnomer, naming it dark energy?
It's a horrible
but it
name.
behaves like a matter.
Yeah, I will be the first to admit. See, mass and energy are the same thing. So mass and energy are the same thing. We just call it mass energy. The reason, see, I put it in a pie chart. Why have I put it in a pie chart? It tells you about the mass energy content of the universe. And in principle, all mass and all energy are interconvertible through equals mc squared, right? So this is the entire mass energy. So this we call energy, because I don't know what it will look like if I convert it into mass. I have no idea. It does not gravitate. Yeah. So give me an equation of state. I will give you the Nobel Prize too if you want.
Sir, can we have that last slide where you showed that big rip thing?
Being unfair to the person who I asked a second question, I did not. Yes, last one, yes.
You said if the universe continued expanding forever, it would result in a big freeze, right? But in this case, that chart, it shows big rip, where atoms are being ripped apart and the Earth explodes.
These are, frankly speaking, these are things that are names people coming up with to match Hawking's names from that book. I wouldn't put too much weight on that. Big freeze, big rip, big whatever. The idea is that the universe is going to become a very, very large place. Much, much larger than what the normal expectation we had from 1980s physics. I don't think the name is that important.
For dark energy, little bit I read about that it doesn't obey the normal laws of matter and energy. Like normal matter and energy, that has a fixed amount. You can only create one energy if you destroy some mass, and vice versa. But dark energy does not have any fixed quantity on the universe. It is making up more and more of itself as time goes along, right? In the direction of entropy.
Absolutely.
So at some point, the amount of dark energy in the universe will be so much that it will rip apart all the big structures.
So what happens is that around this time, dark energy became important. We know that actually in the very early universe, dark energy was not important. So you're absolutely right. It has become important at a certain point. And that, how that evolves is inherent is what has already been said. It's so-called equation of state. It's the relation between its physical properties like pressure, volume, density, etc.
Is it?
What you're doing is you're getting very, very technical now. And you're already starting to lose the rest of the audience. If you want to talk about this, I can talk about this later on. But let me also tell you that I don't have an answer to this. If you take up a volume of Physical Review E now, any typical volume, you will find 30 papers in each volume that has some kind of a prediction for the equation state of dark energy or quintessence or whatever it's called, right, or cosmological constant. So I think we'll have to wait for this whole thing to settle down a little. And in fact, in my institute, there are at least 5 PhD students who are working on various models of dark energy. And worldwide, there are many hundreds of them. So there is no answer. I mean, you can speculate. Why didn't you start a PhD working on doing something like this? Okay. Can I come back to your question because I was unfair to you? Yes.
There are elementary fields like the Higgs field, so that has been experimentally created recently in CERN. So how does that abate to the idea of dark energy?
I don't know whether anybody's made a relation between the Higgs field and the dark. They're two very different things on its in the face value, and that is because we do not have a full picture of the quantum nature of gravity yet. Okay. You know that, right? So the thing is, we haven't put together quantum mechanics, which describes particles at its very small level, and the big picture of gravity. The Higgs field we know in a very good quantum description.
Okay, sir.
Come up with quantum gravity, we will understand that.
Sir,
yes.
there is...
13.8 billion years. 13.78 billion years. Plus minus 0.02. That's another lecture. Let's ask the organizers to ask me to come back, and I'll give you another lecture. No, well, I mean, a very simple way of doing it is, it's not the most accurate way, is I showed you the expansion of the universe, right? I showed you a plot.
Sir, in the last phase...
all you can do, I mean, if you take something like this, something like that, and you know what the expansion of the universe is, and you know the history of the expansion of the universe is that in the past you know how fast it was expanding, you can all, work that out together and figure out how long the universe is expanding for. That gives you. What? Yeah, but we are going to deep space. We're going to very, 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 very far away. And so when you're going far away, we're already talking about 12 gigaparsecs here. We're talking of very, very far away, which means we're looking at the past of the universe. And we know exactly how the universe has been expanding, and the fact that it was expanding slowly, fast, and then it's... So you can actually do that. But there are many other ways of expanding. You can talk to me later. Yes, how many more questions can I take? Oh, 5 minutes more. Okay, yes. I'll come to you.
Here the title of this talk is The Future of the Universe. Sir, why not the future of the multiverse? There is only one universe? Or?
Good point. That's because I don't know how many universes there are. I'm stuck to one. I would love to go to another one. I consider it a privilege when I go to, take a plane and go to America. But, going to another universe would be fantastic. So, so this is a very interesting question. I'm sure a lot of people have questions about this. Let me just, in a nutshell, describe to you. The idea came from a man called Hermann Bondi, who used to be in Cambridge for a long time. He's actually the master of my college, Churchill, in Cambridge. Bondi, in the 1960s, came up with a very interesting idea, saying, look, can anybody explain why the speed of light is 3 times 10 to the 8 meters per second? Why does Planck's constant, gravitational constant, why are the values these values and not something else? And nobody had an answer to this. And he said that the only way you can answer questions, such fundamental questions like this, is that there must be many, 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 many universes in which all these values are different. So here the speed of light is so, and in the universe speed of light. Now, if, for example, you have a universe in the speed of light is 300 meters per second, and the Planck's constant is, 10 to the power 28, that universe will last only 1 second and will die. And there might be other universes in which there will be very long-lived universes, very boring, no stars will form, no humans will form, nothing will form, etc. So there must be many, 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 many universes which have their own characteristics, right? This is the stuff of science fiction. The problem is that we are stuck in a universe because the boundaries of our universe is defined by the speed of light. We cannot travel faster than the speed of light. And so the boundary of the universe means the farthest we can see in the age of the universe, the amount of, the distance through which light has come in the age of the universe. There must be other things outside. So, question was asked, what happened before the Big Bang? Could be there were two other, there has been, for example, if you look at M theory, the famous, Raman and Sundaram, Randall and Sundaram theory of brains, where people say the new universes can be created by the collision of other universes. So it could be that from one universe, another universe comes, and their properties might be related and stuff like that. This is philosophical because there is no way, nobody's come up with an experiment that can actually differentiate between something like this and an alternative. So in physics, that is a problem. If you cannot predict an experiment that will distinguish between alternative theories, it becomes a mathematical exercise. So the multiverse is a very interesting mathematical exercise. And if you want to, I can recommend Max Tegmark's book called The Mathematical Universe, which came out a couple of years ago. It's a fantastic book which deals with this head on, talks about what kind of experiments you can perform. But right now, a multiverse is a very interesting concept, very mathematical concept, right? It might contain answers to these questions like what was there before the universe, what will be there after the universe, things like that. But we are stuck with just one. Yes.
Yes, good evening, sir. And first of all, thank you for presenting us such a wonderful presentation. One very specific question. Let us concentrate on this universe, this one universe. If we consider this universe to be a set of all these galaxies, can we expedite about the geometric shape of this universe?
What do you mean by the geometric shape?
Means if we consider the entire universe with all these galaxies, n number of galaxies, is it a spherical object?
Right.
Or,
so,
yes.
no, well, there are many ways of looking at this. One is you can look at the distribution of the galaxies themselves in the universe. And that I can go back to my very first slide where I had a picture of a simulation of the distribution of matter in the universe. So if you look at what the universe looks like and you take a slice through it, this is a simulation of what the universe looks like. It's actually very filamentary. It has sheets. The galaxies are distributed like that. And we know this is something that we observe now. So this fills space, and in space, the galaxies are not uniformly distributed. They're distributed in these large sheets. We call this the cosmic web because it reminds us of a three-dimensional kind of version of a spider's web. So that's one way of looking at it. Because underlying that is the shape of space. And space, I don't know what you mean by a sphere. It's, because if you're standing here and looking at various directions and the farthest you can look is the amount of light, the distance that light has come to you from the earliest universe, then it is a sphere. But the shape of that space is determined, as I said, by the amount of matter locally. So locally, if you have matter there, the shape of space changes around it. That's why light bends as it comes around matter. And you can look at matter like that. You can then visualize in your head what the shape of space would look like, because space itself would follow the contours of space, would follow these. I mean, I don't know whether that answers your question, but it's probably more than what you asked for. Yes.
Thank you, sir.
Very good evening, sir. Just wanted to ask you something out of curiosity. Sir, whenever we talk about the future of the universe and about finding the answers to a lot of its present mysteries, a topic or a theory that gets the spotlight nowadays is that of string theory. Now, I don't understand anything about that, but my question is that why is it that a group of scientists are dead against that theory while other group are embracing that theory?
Can you think of any field where there will be some people dead against something and other fields, politics, for example? But string theory is a kind of theory. It's a theory of which is a theory of reality that looks at our reality being embedded in a very large number of dimensions. So we live in three-dimensional space, and string theory, various versions of string theory says that actually space is 9-dimensional, 11, 27 or whatever, and we only perceive 3 of them. It solves a lot of mathematical problems, but it has not come up with any experimental verification that will allow you to understand how many dimensions there are, for example. And this is why some people are dead against it. Because they say, what's the point in coming up with a theory that I can't experimentally prove? And the person who does the theory then says, who cares about what experiment you do? It's a very nice mathematical exercise. It explains all these things that you can't explain by other things. That is the answer, short answer to your question. But string theory is beautiful. There are many versions of string theory that are wonderful. The stuff that's done by Ashok Sen, for example, for which he has become very famous. Ashok Sen actually showed that all the kinds of string theory that actually work are the same, underlying, which is a wonderful mathematical theorem that he proved. So there are very wonderful things that are happening in string theory that might, at some point, explain all of these things that we are talking about. So it's a line that is worth pursuing. But currently, the scientific world is divided because there are people who think that I want experimental evidence. Otherwise, you are doing something useless. That's the answer.
Sir, but
I don't think I understood your question, but it's also not related to what I was saying. Inflation, yes, of course, it is related because inflation is something that happened. I didn't talk about it. It must have happened in the initial part of the universe that explains a lot of things that we see in the universe now. For example, the causal relation between different parts of the universe and things like that. So, in short, what we now think is that after the Big Bang, very shortly after the Big Bang, there was a rapid inflation phase where the universe expanded by a huge amount. It's not the same thing as the inflation I talked about now, which is the expansion of the universe that you see now. And that is necessary. That was again a theory that people ridiculed at the beginning, but now we actually have experimental evidence of inflation. Now, as inflation was happening at that point, of course, if the space itself expanded by a very large amount within a short period of time, the curvature of space would change too, if that's what you mean. So curvature of space is related to the nature of space. Yeah, but other than that, I don't think there is an answer to your question. There's one here, but there is no antimatter there. Matter and antimatter would be in the same part, yeah, because they are matter. Antimatter is not. It's matter. So if you have an antiproton, it is the same as proton because it's also made up of quarks. So there is no extra provision of antimatter there. Yeah, except that where we are, we don't find as much antimatter as matter. And that's a puzzle that we have to live with. There might be other parts of the universe where there's more antimatter than matter, whatever. But matter and antimatter are both made up of quarks. So they're part of that pie chart, they will be in that yellow. It's the most difficult question possible. I mean, again, I hope my hands are up. We don't know. This is one of the most, sought after questions in physics. If you come up with the answer, you again Nobel Prize straight away. But it's a very, very important question, and people have been worried about this. Einstein was worried about it. We are worried about it, and we can produce antimatter in the lab, but we don't see it naturally occurring, and I don't know why. Right? Okay. Well, thank you. Thank you for your patience.
Thank you. Thank you so much. Somak, he has taken us magnificently and gently over to the dark side in the end. And so the future of the universe, as Somak has shown us, is not too bright. It's going to be a colder place at the end of the day. But we can always give him a warm applause. So please join me in thanking Professor Somak Raychaudhury. And we have tea outside. And the questions that you have, so many questions, the conversation may continue over tea outside. Thank you very much. Oh, I have a pleasant duty on my part